So I am actually happy to say that this is ManyTones, whose meeting I just missed because I was in a different session. But this is a new project from Many Languages, and Chenzi is going to be here to present to you guys what we're working on.
Um, well, then I think I'll start. Thank you, Erin, for the introduction. And hello, everybody. I'm Chenzi. I'm currently an early career research fellow at the University of Oxford. Um, I will be presenting on the project ManyTones, and hopefully this is one of our very first study on perception of fundamental frequency perturbations across many languages. I have to say that I am not alone in this journey, and I have a lovely team, which I will be introduced right away. I wanted to point it out that I included a QR code on the screen. I realized that I didn't upload the slides on time. So if you are interested in viewing the slides, feel free to scan the QR code so that you can have access to the slide on your own screen. Great. This is our leadership team. I have to say that without all of their support, this project would not go very far. So I am thankful that I have such a lovely team. But these are not the only person in our team. So here you can see the organization structure of our team. So we have a leadership team. That's the purple colored boxes here. And then we also have methods and analysis teams. In the future, we are hoping to recruit more data collection teams and translation teams, as well as a translation lead. Here, I'm just do a small advertisement. So if you are interested in our project, after hearing this talk, feel free to reach out. We can have a talk. So this is the roadmap of today's talk. So it's three main area. I'll give you a bit of broad context for this project, and then explain the very first study, the method, and some pilot findings. In the end, I'll conclude this talk with the timeline of our project and some challenges we have encountered so far. So let's get started. I'll start by saying that pitch is critical in communication. So pitch carries a lot of information in non-human vocalizations as well as human sound and human music. So from this figure, you can see the primate evolutionary relationships. And I have to say that all these most of these species here, they use pitch in their vocalizations, the rises and the falls, as well as in human speech. And pitch can convey a lot of different information. Sometimes could be physical, like to signal the body size of the vocalizer. It conveys sometimes emotional states or social distance. And in human language, in human speech in particular, that it conveys sort of semantic meanings. Before, because I understand the audience is very diverse, so I would like to give a proper definition of pitch and fundamental frequency here, given that this word can be used in various different ways in different fields. So pitch refers to our perception of a sound that's correlated primarily with fundamental frequency. And fundamental frequency, sometimes in short form F0 or F0, refers to the lowest frequency of our vocal fold vibration. So in today's talk, we're going to base on these two concepts. And so quite often you hear people saying pitch and fundamental frequency, sort of to use it in an interchangeably way. And fundamental frequency mostly refers to the physical space, while pitch refers to the sort of perceptual space. And apart from the paralinguistic use of pitch in human language, such as conveying how happy you are or how drunk you are, we can also use pitch linguistically. And we can categorize the linguistic use of pitch in two broad categories. One of which, and the former category, is called macroprosody. So these are the prominent pitch contour shapes used in speech that often spans over syllable, phrases, or longer utterances. And linguistically, we sometimes use phrases such as definitions such as stress, intonation, pitch, accent, lexical tones to refer this type of prosody. And we also have another category, which is called microprosody. So this refers to pitch variation in a relatively smaller time domain, and quite often it is related to segments such as vowels and consonants. I will give you more examples. So first, macroprosody. Here I'm demonstrating what we call lexical tone. So in English, we know that we can say the word cat in various different intonation, and they all refer to this lovely, fluffy mammal cat. But in languages such as Standard Mandarin, for instance, we have this syllable mao, and then it refers to cat. But then if you change the pitch, such as mao, 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 it completely changed the meaning of the word, so it can refer to fur, wooden tenor joints, or a hat. So languages that employ pitch in this way, in a way that changes the meaning of the syllable or the word, is called lexical tone languages. And according to some rough estimates by linguists, more than half of the world's language, or more than about half of the world's languages are tonal. And the broader context of our project is how do these tone languages develop? Then another example of the microprosody. So here I'm introducing you the phenomenon consonant-related fundamental frequency perturbation. CF0 in short. So here I'm illustrating this phenomenon using Bengali data. So you can see that there are 4 Bengali words with the same rhyme, and they have different initial consonant. And the participants are producing these words in isolation, and you can see the measurement of the F0 contour of the vowel portion. So you can see that in the beginning of the vowel, the F0 differs quite a lot. So from this figure, we can see that the F0 of the vowel onset is influenced by different consonant type. In specifically, you can see that the voiced aspirated stop has the lowest pitch in this case, and the voiceless consonant t sound that has quite high pitch in this case. I wanted to say that Bengali is not unique in this case. So here on the screen, you can see a cross-linguistic study on the CF0 phenomena. We can see that all the 20 languages displayed here, they show some kind of CF0 effect. And we can make a generalization that the fundamental frequency, especially at the vowel onset, is higher following a voiceless consonant than following a voiced consonant. So voiceless consonant includes such as patg, sh, or the voiced consonants include badg, examples like that. So what we can also observe from this production study is that the corpus study is that the temporal extent and magnitude of the onset F fundamental frequency perturbation varies considerably between languages. How does the microprosody and macroprosody, how are they connected? So in one of the development of tone, the theory of on the development of contrastive tones is that they are actually very closely connected. Here I'm demonstrating you a model of tonal genesis, the development of tone in 5 stages. So you can see that in the beginning, we have these two words, ba and pa, and they are distinguished by the voicing feature. So one of them is voiceless, one of them is voiced. And then in stage 2, you can see that we observe some what we call it consonant-related fundamental frequency effect, in the sense that the voiceless consonant leads to a slightly higher fundamental frequency onset, or like overall the pitch is slightly higher. And then from stage 3 and stage 4, you can see that the pitch cue is getting strengthened, while the voicing cue is actually diminished. And then in the end, at stage 5, we can see when the voicing feature disappeared, that pitch became a prominent cue in signaling this pair of contrast between initially ba and pa. So from this phonogenesis stage, we can see that from stage 2 and stage 3, we need to at least know that this small fundamental frequency perturbations we observed from production studies, they should be at some point ideally can be heard by listeners, so that they can reproduce the differences and even exaggerate the differences in their production. And from stage 3 to stage 4, we can see that the pitch cue can be one of the cues, maybe redundant in signaling the consonant contrast. So I wanted to show you just to talk about that the both production and perception may be important in this theory of tonal development. So that sets the context for our research. So there are a lot of acoustic studies in the field, and yet not a lot of studies on perception side of the story. So in this project, we wanted to know that to what extent can CF0, like such onset fundamental frequency perturbations, can be perceived. We also wanted to know that sort of how our language factors such as language experience and musical competence affect the CF0 perception. As we know that in the auditory perception world, lots of human auditory perception can be very complex. A lot of factors from age to cognitive functions to language background can potentially influence our perception. So let's talk about our experiment design for the first study. So we are replicating an experimental paradigm used in Ombert 1975 study. So here in this figure, you can see a schematic representation. So we would manipulate the fundamental frequency control of a stimulus. So ideally, it's 250 milliseconds. It's close to the length of a syllable. And then we ask the participants to match the pitch that they heard of the beginning of the stimulus tone using a flat tone. So basically, they have so in the Ombert study at that time in 1975, they are using a knob to adjust the fundamental frequency of the response tone, so that they can match the pitch to the beginning of the stimulus tone. So that's the pitch matching experiment. So in the modern design, we probably don't need to really design a machine with a knob. So we were thinking of turning this into a web page sort of interface where we can use a slider to simulate the knob design. So this is our stimuli. So we manipulated the duration of the pitch slope. So you get a slope that simulates the CF0 perturbation we observed in natural data. We also manipulate the onset frequency perturbation. So it could be larger, it could be small. And here we, in this, the pilot design, we included 6 perturbation duration options and 8 perturbation frequency type. This is our pipeline. So the original Ombert study is tested on 10 American subjects. And I assume that it's quite hard to generalize about human auditory perception based on 10 American speakers. So here we wanted to run a large scale study that also incorporates to be more inclusive, to include to include more language communities as well. So the idea is we would tailor the experiment in a particular language, and then we would collect the demographic information of the participants. We would do some, because ideally we wanted to make this experiment more accessible, so it could be run even online at home if you have a headphone. So we included some basic headphone and sound check. Before progressing to the main part is the pitch matching task. And in the end, we included a module of musical ear test to assess their musical competence before we exit the experiment. So our hypothesis, so the study is very much exploratory in nature, and well, a good educated guess would be that we can observe some kind of categorical effect in perceiving the onset pitch perturbations. In other words, when the perturbation frequency is very small or the perturbation duration is very short, it's quite hard or it's very difficult for us to perceive the onset change. And so we ran this pilot experiment to 36 subjects. And I have to say that these 36 subjects is very diverse in terms of age, in terms of musical competence, as well as language backgrounds. So it's a very diverse audience. And here I'm presenting some descriptive plots to give you a sense of the task. So the first finding I wanted to show you is the accuracy of judging the perturbation direction. So in a sense, if you were given a stimuli with a higher onset, and to see what is the percentage of participants actually perceiving it having a higher onset. So in the sense that they may not hear it, or maybe they hear the input in the wrong direction, so they think it have a lower onset. So so from this plot, you can see generally we observe this pattern that the higher the fundamental frequency onset and the longer duration they are, the accuracy increases, right? So we can pretty much observe this positive trend here. And what we can also observe that when the perturbation frequency is fairly small, like 10 hertz, which refers to the left condition in the plot, you can see that the accuracy maximally reach about 0.3. So the accuracy is very low, even when you have the longest duration, like one of the long duration here, 120 milliseconds. So so we do see that sometimes the longer duration may not help much in recover our judgment of the perturbation direction when the perturbation is very small. And here you can also observe some kind of non-linear pattern in the increase of the accuracy of the judgment. There is another plot. So here we just averaged all of the responses, the perceived frequency from the 36 participants. And then we do also observe this general trend that actually they can, especially with the longer duration and large onset perturbation frequency, they can actually perceive that, yes, there is something changed about the onset. So they can hear this onset perturbation. And in certain cases, such as if you look at the 20 millisecond condition, you do observe some kind of plateau that with increased longer duration in this pattern. And the grayed out plots. So the grayed out color and the lines in these plots are individual responses. And you can see the responses varies a lot from different individuals. There is considerable individual variation. And this is another plot, which is the same, but we sort of represented in terms of by the onset by time. So here you can also see that the response frequency is roughly linear with respect to the onset perturbation frequency, but it only reached that kind of linear status when the perturbation duration is very large. So you can see that when the time the delta t value is about 120 hertz, and if you look at the positive onset condition, you can see that you observe a more linear trend when the duration is large, but you don't see that for instance, the 40 millisecond conditions. So these are some primary observations from the relatively messy group of 36 participants, but I think we can gain some insights about our perception of microprosodic pitch perturbation. So in the end of the talk, I wanted to mention that these are the following steps, and we are writing up at the current stage pre-registered report, and we also are collecting feedback on our pilot studies, and we would hope to improve it before we release it to the larger audience. And in the very end, I would talk about the three main challenges that we encountered so far. So the first is that it's quite hard to model the auditory perception, given that it's a highly complex. So there were a lot of factors would influence auditory perception, and we also observed considerable individual variation. So there are perfect pitch participants. Sometimes you can also get tone deaf participants. In the past study, you also have discriminators and non-discriminators, in the sense that the individual variation can be large, even if their language background is similar. And in the end, it's also a trade-off between the length of the experiment and then the participant number, because we wanted to open the experiment to sort of minority language communities, and sometimes it can be very challenging to find large participant number so that's another challenge. And yeah, that's the end of the talk. And please reach out to us if you are interested in our project, and we welcome all sorts of feedback and suggestions. Thank you much. Thank you very much.
Great job. We have a couple minutes for questions if folks have them. I would ask you more questions, but I finally have gotten, Timo can attest, the F0 idea down. So I think the visualizations are really helpful. And we might want to put some of those in our like GitHub or website somewhere, because it really helps non-sound people conceptualize, I think, what you're trying to measure.
Um,
Questions from folks? So in the chat, we've got other factors that you're interested in, maybe some of the variability that you're mentioning. So are there things that you're particularly interested in, such as the variability, for example?
so I think one of the interesting things for us is that because we make a prediction that our perception is categorical, in the sense that when the delta F and delta T is really small, it's really hard for us to hear it. And I think this is also central to the tonogenesis story. If a tiny microprosodic cue, if they're so small that we barely pay any attention to it or we barely hear it, then it's very hard for the theory to go on, so that that it become a prominent cue in and gradually the language evolve into a tone language. So I think one of the most central thing we are interested in is that we want to test perceptually if the tonogenesis story can be possible under this framework. So we are able to hear the onset perturbation, and ideally we wanted to know that if there is any area or regions in the parameter space, sort of in terms of delta F and delta T, that we are more sensitive in particular regions, that we can hear the perturbation very well, sort of in a consistent manner. I guess that's the primary point of interest. But yes, we are collecting data on language background and musical competence. And I think a very interesting exploratory questions is to see how does our language background influence our pitch perception, right? And how does our musical competence influence our pitch perception? I think that that would be very interesting to explore. For instance, we in our team actually we have some kind of prediction, in a sense that we seem to observe that tone speakers, so tone language users, they might be better than non-tone speakers in this particular task. But that's not that's just something based on very small data set from our observation. But it'll be interesting to see how our language background influence our pitch perception.
Can I ask another question real quick? So right now it looks like even in the longest slope duration and even with like the biggest frequency chain shift, folks aren't at ceiling. Are you planning to like expand it out to like the range of stimuli to get to that ceiling, do you think? Of like, okay, we know that folks reliably detect a shift here, or does that question make sense?
Yeah, I wanted to mention that the ceiling, so the response frequency we get, I can show you the maybe this graph. So we actually have a condition of 200 millisecond, 250, which is the total length. So basically the whole slope is the whole thing is a slope. We do have that, and then the accuracy is also increasing, but it was never fully 100%. And
Interesting.
yeah, and I wanted to also mention that this task can be quite difficult. If you we can provide you the experiment link to try it out. And perceiving the absolute delta F is impossible, because that's related to how we perceive a slope. So according to the psychoacoustic literature, we tend to perceive the whole slope in a holistic way when the duration is short. So we hear one pitch instead of the whole slope. We don't perceive it as a slope. And in that sense, we also tend to perceive it sort of 1/3 of it. So in a sense that the ceiling, even if the delta F can be 40 Hertz, the response may be just close to 10 Hertz. So you can see the average value here that I cropped the y-axis range to -10 to 10, just to show you the pattern more clearly. But you can see that that's the kind of range people on average can go, even if it's 40 Hertz delta F. But there are a lot of individual variances. There are some responses which is cropped out here, not shown, that goes quite high in the response. Yeah. Thank you, Corey, for your question.
All right, so we're at time and gonna pop over to the next session. So thank you, everyone, and I will we'll share these as part of the conference slides, and so you'll be able to see this presentation again later if you need. So appreciate everybody attending.